This video is on alkynes, which is chapter 9 in our textbook. I'm going to mainly discuss in this video regarding some methods of preparation of alkynes and reactions. But before we talk about the preparation and the reactions, let's classify the alkynes into terminal alkynes and internal alkynes. Internal alkynes are where the triple bond appears somewhere within the chain of the carbon atom, and terminal is when it appears at the end of the chain. So for example, this would be a terminal alkyne. And also remember that when you count the number of carbon atoms, you have to include the 2 carbons at the triple bond. So this is a 3 carbon atom chain, and it will be named as 1 propyne or just propyne. And this one is actually a 4 carbon atom chain, 1, 2, 3, and 4. So it is a butene, and then at the second position we have the triple bond, so it is 2 butene. Okay, regarding methods of preparation, alkynes can be prepared just similar to alkenes by using alkyl halides. So just as in if you recall in the previous chapter for the preparation of alkenes, we had used a alkyl halide and treated it with a base like potassium hydroxide or sodium hydroxide, sodium amide, soda amide, and this resulted in the formation of an alkene. Okay, so you just need a strong base. And same thing in case of alkynes, but now we need 2 degrees of unsaturation, so we will have to use alkyl dihalides instead. Okay, so for example, I can say RC, can have a Br here, a Br here, hydrogens here. Okay, and when I treat this with a strong base like potassium hydroxide or soda amide, this results in the formation of a triple bond. The side products are, if I use KOH, then my side products will be KBr and water, H2O. Okay, here I would need 2 equivalents, so I'll get 2 KBr and 2 H2O. Why 2 equivalents? Because I have to get rid of 2 bromine groups in order to form the triple bond. You can also do this with the halogen groups on the same carbon atom. So for example, you can use a compound like this, where both the bromine atoms are on the same carbon atom, and then again you use a base like say KOH again. This results in the formation of a triple bond similar to the previous example, and again the side products will be KBr and H2O. So this is a good method of preparation of alkynes from alkyl halides. So the other base which you can use, example of other strong base, can also be NaNH2. Okay, sodium amide, this is H2. Okay, so this is also a strong base which can be used for the preparation of alkynes. Now, regarding the reactions of alkynes, I will discuss a couple of important reactions in this video, starting with reduction of alkynes. So alkynes will undergo reduction reaction very similar to alkenes when you treat them with hydrogen in palladium. Okay, so if you recall, for alkenes, I'll write it here, that if you take an alkene and react it with hydrogen in presence of palladium over carbon, you can reduce that to an alkane, right? Similarly, in case of alkynes, if you take a alkyne and react it with hydrogen in presence of palladium over carbon, you can end up in the formation of an alkene. Okay, so we have 1, 2, 3, 4 carbon atoms, and you have 4 here, so you can end up in the formation of an alkene. Okay? However, there are some variations to this reaction where if you treat the alkyne with what is called as a Lindlar's catalyst, okay, which is palladium over barium sulfate. So we will do reduction again. It's also a reduction reaction, so let's call this as A. And then the next reduction reaction, where I treat this same alkyne, okay, same alkyne with hydrogen, but then it is done in the presence of Lindlar's catalyst. Now Lindlar's catalyst acts as a poison, catalytic poison, as a result of which you can stop the reaction and in the alkene stage rather than taking it all the way to an alkane. And the other characteristic feature is that this will form a cis alkene. Okay? And then if there is no further reaction to it, you cannot react it further, so you can actually stop it at the cis alkene stage. It is cis because, see, we have the 2 hydrogens cis to each other, right? So this is cis alkene. However, if you want to get a trans alkene, there is a different method we use, and that is by using lithium or sodium in liquid ammonia. So it's a metal reduction reaction. Okay? So I will use the same alkyne to illustrate that. So we have a butane, 2-butane, and if this is treated with sodium or lithium, okay, so you can use either one in liquid ammonia. What you can get is a trans alkene. So you can stop the reaction at a trans alkene stage. So here, see, the hydrogens are trans to each other. So these are the 3 methods of reduction reactions of alkynes. One is when you treat it with hydrogen over palladium, just converts it into an alkane. You have no control of this reaction. The reduction will happen till all the triple bonds are saturated to form the alkane. Okay? And then here we have a reaction where if you treat the alkyne with hydrogen, but in the presence of Lindlar's catalyst. And Lindlar's catalyst, like I said, Lindlar's catalyst is palladium over barium sulfate. Okay, that is Lindlar's catalyst. You don't have to write this down. You can just write Lindlar's catalyst, and that would be enough. But the resultant product is important, that you get the cis alkene. And then the final one is the reaction of an butane with sodium in liquid ammonia, and it forms the trans alkyne. Sorry, as an alkene. Okay. All right. So you are expected to know the mechanism of this third reaction. So we will do that in the next page. So the first step in this is actually a radical reaction. So the first step here is where you can say, I take this example, okay, CH3, C, triple bond C, CH3, 2-butane, to illustrate this. Okay. The first step is where one of the pi bonds homolytically cleaves and you get a radical, and sodium or lithium, either one of them, they are able to donate a single electron because they are electropositive elements, right? They are the metals, like to donate an electron to get the noble gas configuration. So sodium donates one electron, and what we get is a intermediate, which we call it as a anion radical. Okay, so see, we have two electrons, one from sodium, one from the pi bond, and this gets a negative charge, whereas this carbon will still have the radical. So this is abbreviated as a radical anion. Okay, radical anion, because one carbon has a one radical and the other carbon has a negative charge. The next step is the role of ammonia. So ammonia provides the hydrogen. So this carbon atom is going to take up one of the protons. So we put the electrons here, and the way the proton will sit on this carbon atom is over here, and then, oh sorry, I forgot the CH3 here. Okay, CH3 here, and then this carbon atom still has the radical, and then it has got the other CH3 group. Okay, all right. So now the another sodium atom provides an electron with this carbon atom, and now we get this carbon with a pair of electrons. So now it becomes an anion, double bond C, and we have a H and a CH3. Correct? Okay. Now here again we have the role of ammonia. Ammonia provides a proton. So this takes up the proton here, puts the electron here, and now since the trans arrangement of protons will be the most stable one, so we will have the other hydrogen sit trans to the previous one, and now our final product is formed in this manner. Okay, so that's how we get the trans alkene. Okay. So this illustrates the formation of trans alkene from an alkyne using sodium or lithium. Okay, so this reaction can happen either with sodium or lithium in liquid ammonia. Okay, ammonia is important because the hydrogens are coming from the ammonia. Okay, so this is one of the important reactions of alkyne. The next video will talk about a few more reactions.